So in today's video, we're going to continue to explore this concept of when is different actually different or statistically different. So basically, we will be continuing on with the theme of alpha of 0.05. Alpha of 0.05 is completely arbitrary. What we mean by that is that's something that we've agreed on basically as a science, but there are times to set it differently. So at times alpha might be 0.01, it might actually be 0.10, but again, generally speaking, you see alpha of 0.05. So going back to the idea of the houseflies, we've caught the 25 houseflies, we've measured them, we've done descriptive statistics. Since we're only dealing with those flies, we'll call those a population. We know what their average wing length is and all that. But in all of this, the researcher has caught all of these 25 flies, but then later he notices that there's been one fly that has been living in his terrarium. And as he notices when that fly lands, it seems that that fly is actually abnormally or unusually large, and so the flies therefore, of course, seem unusually larger than the rest of the group of the flies that he caught around the house. So now he begins to wonder two things. Are the wings on that fly actually different or actually substantially larger than the rest of the flies in the house? And so he measures the wings and finds them to be 5.1 millimeters in length. So we now know the length of the wings on that fly, but we don't know if they are statistically different. But that also leads him to the second question is, well, if this fly is actually different than the rest of the flies in the house, then is it possible that that environment in the terrarium is what caused that fly's wings to be larger? Or another way of saying this is the environment in the terrarium such that it actually allows the flies or causes the flies to grow larger? Or is it just random chance that this one fly that was in the terrarium just happens to be larger and the terrarium, the environment in the terrarium, actually has no effect on the development of the flies? So remember, we need to go back to talk about what we did in the last one, converting things to a standard normal distribution. Well, the standard normal distribution is unchanging, it's statistically set, and so we know a few things about it, and this helps us think about it. So remember before we talked about that alpha of 0.05, or 5% of the area under the curve. So the entire curve is 100%, we're talking about 5%. But since we're going to divide that into the two tails, we're actually talking about 2.5% in each tail. Well, we had talked about standard deviation in previous videos. We'd learned how to calculate a standard deviation. Again, a standard deviation is, on average, how far away do we expect an observation to be. I actually have a mantra that I teach in my classes. I make my students memorize that mantra. I actually encourage you to memorize it as well, because it will very much help you as statistics get more complicated later. So the mantra that I have them memorize is standard deviation is conceptually the average distance of an observation from the mean. And that one observation from the mean is going to become important because we will have other mantras that are very similar but slightly different later. So again, what's the average distance that we expect an observation to be from the mean? That's the standard deviation. When we convert to a standard normal distribution, what we find is that the average, the center point in a standard normal distribution is 0. It will always be 0. Then the standard deviation for a standard normal distribution is always going to be 1. So if something is one step below, or an expected deviation below, that would be -1. But if we go to the positive side, a standard deviation is going to be +1. As it turns out, when I divide that 5% into the two tails in a standard normal distribution, it's almost two standard deviations above and below. It's actually plus 1.96 and negative 1.96. I encourage you to memorize that because anytime that you're dealing with the standard normal distribution, those are what are known as critical values, and it's going to be plus and minus 1.96 if you're doing a two-tailed test. So to convert now that length of the wings on that one fly into a standard normal score, we know those as z-scores. So we have to convert that into the standard normal z-score, and the formula for the z-score is, as you see it here, the z-score is going to be z, and then we have x, and we're going to talk about these what these are soon, minus mu divided by standard deviation of that distribution. So let's start with question number 1. Are the wings on that one fly that he found in his terrarium actually substantially larger, statistically larger, than the rest of the flies that he captured in his house? So as we said, the measurement there is 5.1. So first we have to convert that measured score into a z-score. Again, it seems ridiculously easy at this point, but I encourage you to build the toolbox, develop that habit, and then we need to copy those values. So first, the thing that you want to do is disintegrate that formula into your toolbox. So we have the z formula. What are some of the subcomponents of it? We have that x value. We're going to put that over here into our toolbox. We also have mu. We're going to drop that into our toolbox, and then we also have standard deviation. We will drop that into our toolbox. Then we ask ourselves, do we have the values for each of those variables that we put in our toolbox? We already said that our individual x value, our individual observation, the fly in the terrarium, is 5.1 millimeters. From the previous videos, we determined that the mu, the average length of the wings for the rest of the flies, all of the flies in the house, was 4.5 millimeters, and we had calculated the standard deviation of all those flies earlier at 0.2. So now, once we have those values, we can then pull them into the formula that we have, the z formula as indicated. So again, the average is going to be 4.5 and the standard deviation is going to be 0.2 as we had talked about before. So once we plug them into that formula and do the division, then we come up with a z-score for that fly. We converted 5.1 into a z-score of 3. But we have to get back to that first question. What the researcher is asking is that fly part of the regular population, or is that fly that we found in the terrarium substantially different, statistically different from the rest of the flies? So with z equals 3, we have to convert this into a scientific hypothesis. We use what are known as the null and experimental hypotheses. The experimental hypothesis is sometimes known as the alternative or alternate hypothesis. The null is indicated by h sub 0 and states that my suspicions are not supported. So effectively what we are saying for the null hypothesis is the length of the wings on that fly in the terrarium is statistically equal to the length of the wings on the flies in the rest of the house. But my suspicions were that, well, maybe the terrarium is different. Maybe that causes or contributes or allows flies to grow much larger. So that's my experimental hypothesis, and this is h sub 1. It's also my working hypothesis. So what we are basically saying in this case is no, because the environment in the terrarium is potentially, hypothetically different, then the wings of the fly in that terrarium are statistically different. They represent a different group of flies than the flies in the rest of the house. So when we write this formally or in statistical notation, we want to write it both statistically in the notation of stats, but then also the language of statistics. So we are saying in the null hypothesis, x, my one fly, equals mu, the population to which I'm comparing it, and so we can literally write that out as the wings of the fly, the one fly in the terrarium, are statistically equal to the wings on the flies in the rest of the house. Whereas again, in statistical notation, the experimental hypothesis is that the wings of the fly in this terrarium are statistically different than the wings of the flies in the rest of the house. I want to give you a little bit of a hint. Notice that I've got it in statistical notation, x equal mu. For many statistics, when you're trying to figure out what to write in the statistical notation part of the null and experimental hypothesis, simply go to the original formula, the numerator of the original formula, and you will find what that formula is asking. We are talking about an observation, x, and we are talking about a population mean, mu, and then just ask yourself, what is this saying? Well, what's my one observation? The wings on the one fly. What's my population? The wings and the flies in the house. So if you just think about what that is indicating, that will help you write the actual language for both of your hypotheses. So moving forward, we have now the hypotheses. We've computed the z-score to be 3. We now want to plot that on the standard normal distribution. In the standard normal distribution, for a two-tailed test, there is also a one-tailed test, which I'm not going to cover in this video. Check your textbook if I don't end up posting a video on it, but it's very much the same. We just shift all of the alpha into one tail or the other, not splitting it into both. So when we have this, we basically have two regions. We have the center region. This represents expected by chance, the normal population. So if our z-score falls here, basically what we are saying is even though it looked like that fly was larger, it actually is statistically the same as what we would expect by chance. But then when we get into the tails, this is what we call the reject region because we're rejecting the null hypothesis. Remember, the null hypothesis said that they are essentially the same. So if we fall into the tail, we are rejecting the null hypothesis. I know it's double negatives, it gets a bit confusing, but we are saying that no, they are not the same. We're rejecting that statement that says that they are the same. In this case, our z-score was 3, so we are falling in this tail, the positive side of the distribution, so we are rejecting the null hypothesis in favor of the alternative hypothesis, and the alternative hypothesis says that the wings on this fly are not expected by chance. They are statistically different than all the rest of the flies that we measured in the house. So what does this mean? That means that by rejecting the null, this fly, effectively, the data collected from this one fly supports my suspicion that it was bigger, and this does beg the question now, is it something about the terrarium? Or is it possible that this one fly just happened to be larger? So really, we would want to do this in a more sound experimental methodology instead of just happening to find one fly. So as we move forward to future videos, that's what we will be doing, is moving on from a statistic for one observation to a statistic for a group of observations and a true experimental design. I hope that you've enjoyed this video and that it's helped you understand. I encourage you now to move on to the video which is going to be a z-test for a group of individuals.